In this video, we will be finishing up the orientation of our character while it's moving, as well as fixing a few nooks and crannies to get a nice polished result. So in the previous video, we left off in a state where our character can move around, however it doesn't rotate towards the direction of the movement. So we gotta fix that. And the way we can do that is, remember we have this visuals node, which has our body and our visor. We can rotate this node around its y-axis, which is the vertical axis. You can see it on the gizmo up here. And if you imagine y stands for yaw, that's a good way to memorize which axis we want to use. And to do that, we can grab it in code by using onReady. We can call it visuals. It's a node 3D, and we do $visuals, as this is the name of our node. And then, since this is not a physics related process, I will just put it in the process function, which is another built-in function in Godot, which fires off every frame. And to demonstrate what it does, let's say we want to rotate our visuals around the y-axis, so we want to yaw it, and I'm just going to be adding 2 pi radians, so that's a full circle each second. So if I do 2 pi delta and start the game, you will see that our character now rotates around its vertical axis 360 degrees per second. So all we gotta do now is figure out how to rotate it in the correct direction, and to do that we're gonna have to dig into some math. So let's start by drawing a coordinate system, and I'll mark this as x and y, and then I'll draw a unit vector at a 45-degree angle. In fact, I will draw 4 of them, like so, and then I'll mark the x and y components like so, which will be 0.707 on both sides, and I will prove that to you in just a second. So we are interested in finding this angle. I'll mark it as alpha, and there is a trigonometry function called tangent, and it says that tangent of an angle is equal to the ratio of its opposite side, which is on the y-axis here, over the adjacent, which is on the x-axis, so y over x, and in this case that is 0.707 over 0.707. However, we already know our velocity vectors, in this case y and x. We are interested in the angle, so we can use the inverse tangent function, arctangent, and we can call it atan. And what atan takes is the ratio of the sides, and it spits out the angle. So we can use this to calculate our angles, and let's jump into Excel and do some math. So here we are in Excel, and I'm just gonna write our x and y's as 0.707, and then here we'll be using the atan function to calculate the angle. So if I use the equal sign and write atan, there's a function that is gonna give us our value in radians, and we wanna pass, as we established, y over x, and this is not 45 because it's radians, so let's also add the degrees conversion, and that way we can see that the angle is now 45 degrees for this first vector. So it's plus 45 degrees, which means it's counterclockwise from the x-axis. And then we still have the other 3 vectors we want to take care of. So we have 4 quadrants. In this first one, both the x and y are positive. In this lower right, we have positive x but negative y. Here they are both negative, and then in the last one we have negative x and positive y. So let's write all of those in Excel. So plus and minus, then both negative, and x negative and y positive. So the second one is minus 45 degrees, which means we are measuring clockwise. So this is minus 45. Then the third one is 45 again, so it's counterclockwise from the negative x-axis, 45 degrees, and then the last one is again minus 45. So this is an issue because we can see that 2 of the angles on the opposite sides can be the same, and we cannot have that in our game. We need to have unique direction depending on our movement. So the problem with atan is that it gives us an angle from 0 to 90 degrees, whereas our character can move 360 degrees, and we can use atan 2, which instead of taking just the ratio, takes both x and y as parameters and gives us a number from 0 to 180 degrees. And with this, we can represent the movement all the way on the plus 180 and negative 180, giving us a full 360 degrees of freedom. So let's use atan 2 here and do exactly the same thing. We're gonna use degrees to convert from radians, and then instead of using atan, we use atan 2 and pass x and y. So now for the first angle we have 45, so that would be this one. The second one is negative 45, so clockwise in this direction, which makes sense. The third one is negative 135, so all the way to here, negative 135, and then the last one is positive 135, all the way to here. So now that we've established a way of calculating our angles depending on our movement vector, we can go back to Godot and write some code. So let's declare a value called target yaw, which will be the atan 2 of, and here it wants to pass y and then x. So if we pass our velocity vectors, y first, followed by the velocity x, and then set that as our angle and start a game, we will see that we get something that is very broken. And the reason for that is the coordinate systems are not equal. So let's go back to our drawing and figure out which components of our velocity we need to use to get the correct angle. So what I'm gonna do is draw this xy coordinate system looking at it from a perspective. So let's move this up a bit, and this is our forward x-axis, and then this is our y-axis. So let's mark this as x and this as y, and let's construct this little blob, which is our character, with its little visor pointing out, looking in the forward direction. So we can see that in this system, x is forward and y is to our left. And if we go to Godot and look at our gizmo, we can see that forward is the negative z, and then to our left is the negative x. So we gotta replace those with a negative z and negative x. And that way we will have the correct orientation of our character. So if we go back to our code, and instead of passing y and x, we are actually passing negative x and negative z. So negative x and negative z. And if we try to run our game now, we see that as we move around, the character also rotates in the correct direction. The small issue here, of course, is if I stop moving, he just starts looking backwards. And we will fix this in a second. So to fix this issue from happening, we gotta make sure we only calculate this angle and set it once that there is actual movement. So let's declare a variable called horizontal velocity, and we're gonna construct out of our velocities x and z components. That way we can say if horizontal velocity, and now we can call a vector function length, or actually I'm going to use length squared because it's a faster function. You can see that in description here. And I'm going to say if it's greater than 0.001. I'm not going to use 0 because once we do divisions and we get to a number close to 0, we can get some really wonky results. So once it's greater than 0.001, then we can calculate our target yaw and set our visual rotation to that yaw. And if we play our game now, you can see that our character is not facing backwards, and once I move around, it's orienting to the right direction. However, you can see it's very snappy, and the reason for that is that we are setting the angle instantaneously. What we can do instead is do something called lerping, which means we will slowly move towards a target value instead of setting it in one go. So to lerp to an angle, we can use a function called lerp angle, and what it wants is from, to, and a weight. So we want to lerp from an angle, which is, well, our current rotation. So you can just copy this number in. We want to lerp to our target yaw, and then with the weight, we choose how fast we are rotating. I'm just going to go with delta times 15. And that should give us a pretty good smooth animation. So if I now move around, you can see that we are not snapping to the orientation directly, we are slowly moving towards it, and that makes everything smooth and nice. Now we still have two small issues that we gotta fix. One of them is that if I look straight down, you can see that our movement is incredibly slow. In fact, I can even move all the way upside down and move our character this way, which is not great. And the other problem is that if I rotate our starting position and I press forward, well, nothing really works. Everything is just broken. So let's fix those two issues and we'll be good to go. So let's start by fixing this initial orientation. So the problem here is that we are using this basis for our movement, and we are using the rotation for our, well, rotation. However, since our character was initially aligned with the world axis, everything worked fine. But once we rotate it, its forward axis and the world forward axis are now misaligned. So things break. The fix is very easy. Instead of using the basis, which is relative to the parent node, so our character root node, we can use global basis. And now it's the basis relative to the world. And same goes for our rotation. So the rotation is relative to our parent node, but if you use global rotation, then it's relative to the world. And we can use the same thing. So now we are using the global values. We go back to our game and press play. We can see that now everything works no matter from which position our character is initially oriented. Now let's fix the issue with being able to rotate our camera beyond the 90 degrees up and down in pitch. To do that, we can simply take the X rotation of our spring arm and say it's a clamped value of itself. So in case we set it to over 90 degrees in the line before, it will now be clamped to a certain number. In our case, we want 90 degrees up and down. So 2 pi radians is 360 degrees, which means pi radians is 180. And then finally, pi over 2 will give us 90 degrees. So minimum minus 90 and maximum 90 degrees. And if we go back to our game, if I try to rotate our camera beyond 90 degrees up or down, it simply won't let me go. So there is another issue fixed, and let's fix the final issue of our speed being dependent on our pitch. So the main problem here is that we're using our spring arm's global basis to define our directions. And what do I mean by that? Here I have a drawing of the world coordinates, the spring arm's basis in the red. The XYZ here is our input vector. And we know that we stored our forward and backwards information in the Z component. What does forward mean? Our input vector doesn't know if forward is in this direction, or in this direction, or in any direction in the world. So when we multiply it by the basis, we are mapping our Z's to the basis Z, and same for the Y and X. So if I press forward without yawing the camera, I would move in the direction of the basis Z, which translates to the world's Z as well. If I then yaw the camera around the Y-axis, then our picture looks something like this. And if I press forward from this position, I would move a little bit in the X-plane as well as in the Z-plane, which is fine because that's what we are using to construct our velocity vector. The problem arises if we pitch the camera, which means rotation around the x-axis. If we pitch our camera by 90 degrees and look straight into the ground, then we get this as our basis. So now our Z is rotated 90 degrees up, so it's facing in the world's Y direction. Our Y faces in the world's Z direction, and the X stays the same. So now when I press forward, the data is stored in the up direction. So that's the world's Y direction. And here we are using Z. So if I replace this with a Y, you will see that if I pitch all the way down, we are now suddenly able to move forward and backwards without a problem. However, we then lose that freedom when I point the camera this way. So what is the solution? The easiest way to do this is to construct our own basis, which is aligned with the world, and then simply rotate it around its vertical axis to match the yaw of the camera. How can we do this? We can declare a variable, we can call it yaw basis, and use the basis constructor, which would create a basis that's aligned with the world. And if we inspect it, there is a constructor that takes an axis and an angle as parameters. This means we can rotate our basis around a certain axis by some angle. So we can simply say we want to rotate it around vector 3.up, which is our Y component. So we will yaw the basis by the amount of the camera's yaw. And if we then use our own basis instead of the spring arm basis, and we replace our Z back to Z, then we can see we are able to move in all directions, no matter what the pitch of our camera is. And with that, we have a fully working third-person character movement. Hopefully this gave you some more insight into vectors and math operations and the fun stuff you can do with them. And if it helped, please subscribe, and I'll see you in the next one.